Hello, this and my other YouTube videos are extracted from the History of Man series, currently 6 books published in print, ebook, and most importantly, audiobook. I'm a storyteller, and if you like these video stories, you'll love the History of Man series audiobooks. Great for commuting or just sitting back and relaxing. And unlike a novel you've read where you know the ending, you can listen to these books on tape more than once. There's so much to learn. Available on Amazon and audible.com, I narrate the audiobooks. And the best part about that is you can listen to these stories without having to look at my stupid face. And with that said, let's get the show on the road. Hello, John Bershoff, History of Man series. Today's subject, Serendipity, Part 1, Discovery of Radiation. Now, before discussing radiation, a definition of luminescence is needed, as it and radiation are often confused. Luminescence, sometimes called phosphorescence, since phosphorus was probably the first and maybe the best compound or element that luminesces. Luminescence occurs when an electron in an atom or compound gets kicked up to a higher orbital shell. When it drops back down, it gives off a puff of light, or luminesce. So you got like phosphorus, which usually on our planet comes with 4 atoms of phosphorus. It hit by light, and that light kicks up electrons into higher orbit. And when those electrons drop back down to their happy place, they give off a puff of energy in the form of light. It's like 1 photon of light kicks up 1 electron. It's similar in principle to solar panels, the photoelectric effect, which actually was explained by Einstein. A single photon of light kicks up a single electron in the solar panel. When it drops back down, well, in the panel, it's converted into electricity and stored, so later it can horsepower your coffee machine. It's also the basis of the concept of quantum mechanics. 1 photon of light kicks up 1 electron. It's a quantum reaction. Luminescence and fluorescence is used in watch dials and inside the lining of a fluorescent light bulb. And we'll get to that in a moment because they're fascinating. Radiation is way different. Now, spontaneous radiation is the emission of an extra neutron from the nucleus of an atom. Radioactive decay. Uranium-235 is the classic one. For bombs, it has 92 protons and 92 electrons, but not in this universe does it have only 92 neutrons. It has 143 neutrons to keep the protons from killing each other. Now, many atoms, particularly the smaller ones, have the same number of protons and neutrons. That's what we're taught. Like oxygen has 8 protons, 8 neutrons in the nucleus. Or carbon has 6 protons and 6 neutrons in the nucleus, although there's a small amount on our planet of carbon-14, of radioactive carbon-14 with 2 extra neutrons. It's not very radioactive, but it does jettison them as beta decay. And it's the half-life that can then be used for radiocarbon dating of things from 50,000 years ago. As atoms get larger, though, the nucleus seems to need more and more neutrons to counteract the repulsion of protons to each other, to keep those protons from annihilating each other. Radioactivity was discovered by accident, by serendipity, although when discovered, the discoverer hadn't the foggiest clue what was happening. It would take Madame Curie to explain it. But let's get into the story. In 1895, German physicist and engineer Wilhelm Roentgen discovered what he called X-rays. He called it X, not X as in Elon Musk changing the name of Twitter to X, but in those god-awful algebra equations, X equals something. He did not know what this ray was, so he gave it the value X, and it stuck. It never got its own name. It always stayed as X-ray. By the way, Musk and pals, I understand, changed Twitter to X because Twitter was no longer a 140-character tweet. Twitter had expanded into an app that did much more. It had multiplied, and that was their X, multiplying. But anyway, back to Roentgen. He was studying a cathode ray tubes and anode ray tubes, and he was curious about the energy coming off them, what they would do to various compounds, although the energy coming off them was unknown. It was known there was energy, but what it was unknown. Now consider this, and this is our fluorescent light bulb. The fluorescent light bulb was invented much later, after Roentgen, but it helps us understand. When high voltage electricity flows along a fluorescent bulb, a filament like tungsten within it, within the sealed glass tube, contains argon gas or mercury vapor. But the electricity going along that tungsten fluorescent bulb excites electrons in the gas vapor to higher orbital shell. When the electron drops back down in those compounds, in the mercury, in the argon, it gives off ultraviolet light. Now that's not luminescence yet, but we can't see ultraviolet light. So if the tube ended there, the light tube, we wouldn't be able to see it. We don't see the ultraviolet. So there was a second step that needed to be added, the luminescent step of fluorescent light bulbs. So along the inside lining of fluorescent tubes is the fluorescent part or the phosphorus part. So you got your tube and you got your electricity going along it, high voltage electricity, and it excites the vapor, the mercury vapor. And the mercury vapor then elevates its electrons to higher energy state. And as its electrons drop back down, it gives off ultraviolet light. But of course, we can't see the ultraviolet light. So the lining on the inside lining of those tubes has phosphor or some type of phosphorescent material. And the UV light then kicks up the electrons in the phosphor tube, and the phosphorus then, its electrons drop down and give off a photon of visible light. So it's a two-step process in fluorescent bulbs. But back to Roentgen. He knew none of this. He did not know the cathode tube thingy gave off. He knew it gave off energy, but he was curious what that energy did. He didn't know what the energy was, but he was curious to study what it did coming off the cathode tube, that he could not see this energy. So he built a light-proof cardboard box, a black box within which was his cathode tube and a tiny peephole, so he could then put stuff in it and see what the cathode tube energy was doing to the stuff in the box. He turned on the electricity, but he hadn't yet placed anything in the box. He was just studying it, his black box, and he was testing the system, making sure nothing was coming out of it, no light. Or so he thought. As he was messing around setting up his experiment, he noticed off to the side, off on his desk, a faint glow. The glow was coming from a chunk of barium he was likely using as a paperweight. So here he is, his black box, something was coming out, some type of, turns out, X-ray, and it was hitting the barium, and the barium was, its electrons were jumping up, and when they bounced back down, it would glow. And that's what he was noticing coming off his thing. Now this is like, he had sleepless nights when he saw this barium glowing. He didn't understand what was happening. And it took much deliberation, and he was barely eating. He was frustrating his wife. And then he deduced that something that he could not see was of such a short wavelength that it passed through his cardboard box and was striking the barium, causing it to glow, to luminesce. He called it, of course, as we know, X-ray, because he didn't know what the ray was. Obviously, as this story goes on, the X-ray emitting from the box was bumping electrons in the barium, and the barium was giving off a puff of visible light. He then had some photographic paper, which is paper that is exquisitely light sensitive, material coated onto it, the most common of which is a silver halide. And when light hits it, when the silver and halide separate, the silver blocks light, and what it gives is a dark film, which means that the dark is white and the light is black. And that's how photographic paper works. By the way, photographic camera uses film, not paper, because it's a negative image. You're always wondering why the film was a negative image. Well, apparently that reaction of the film is much faster than the positive reaction of photo paper. So when you're taking a picture with your camera and you have a fast shutter speed, well, you need film because it reacts within seconds, whereas photo paper could take minutes to react. In fact, it was in 1802 that Thomas Wedgwood invented photo paper, and it was 1885 where George Eastman, you guessed it, Eastman Kodak, invented photo film. Obviously, the photo film, you then reverse the image onto photo paper. Photo paper cameras, they were actually around 150 years ago. They didn't have film. It's like that guy with that thing on the tripod and he has a black cape over him. He's probably using photo paper and needed long exposure time. And the people had to sit there and not move for who knows how long, a minute, whereas photo film captures within fractions of seconds. But back to our story. Roentgen apparently placed his wife, Bertha's hand on top of the photo paper he had and exposed it to this cathode ray tube thingamajig box he had built. And over time, I don't know, minutes, it imaged out her hand. It etched the bone. It was the first X-ray ever taken. It was 1895. Also in that year, French physicist Henri Becquerel was messing around with some uranium salts, probably uranium-238. And what he was doing with that uranium is unclear to history. But what is clear is he placed his uranium rock into a drawer on top of, you guessed it, some photographic paper and closed the drawer. Sometime later, he opened the drawer and initially, to his dismay, his light-sensitive, likely very expensive photo paper was ruined, despite being in a light, tight drawer. The photo paper had reacted with something. Now, after some deliberation, he correctly deduced that the uranium was emitting some ray that he could not see, but was certainly reacting with and messing up his photo paper. This was spontaneous radiation by Becquerel, whereas Roentgen, his radiation was produced by high energy electricity. This was spontaneous radiation. The uranium was emitting something and that it was reacting in that way. Now, Becquerel correctly deduced that the rock was emitting this ray, some type of energy. He did not know what it was. He did not have to put electricity into it like Roentgen's cathode tube. The uranium was apparently spontaneously decaying, but he didn't even know that. He had serendipitously discovered spontaneous radioactivity, although it would take Madame Curie to explain it to the world. And by the way, just to give you an idea of what type of radiation we deal with, alpha radiation are high emissions of helium nuclei. Beta radiation are high energy electrons, also called positrons. Gamma radiation, which gave us Bruce Banner, the Hulk, are high energy photons, really high energy. And X-rays, like these experiments, are high energy photons, are also gamma radiation, are X-rays. They're just not quite as high as gamma rays. So now into our story steps Madame Curie, born Maria Solomia Sklodowska in 1867 in Warsaw, Poland. She moved to Paris at age 24 and in 1891 received her formal education in physics at the University of Paris, which is also where she met Pierre Curie and married him in 1895. But Madame Curie discovered the radioactive elements radium and polonium, which is named after Poland, in 1898. But important to our discussion, Curie also deduced that radioactive elements, uranium, radium, polonium, and others, were not emitting radiation by a chemical reaction, certainly not by electricity, as was the convention at the time, but that something inside the atom was emitting energy in a precise, rhythmic fashion. Now, conventional wisdom amongst physicists the world over at that time was that atoms were invincible, indivisible. Her theory that they were not, that the atom, likely the nucleus, was decaying, was emitting something of itself smacked against the laws of physics. As an aside, it was in 1897 that J.J. Thomson, a Brit at Cambridge, discovered electrons by demonstrating that the cathode tube had negative charged particles or electrons coming off of it. It was in 1917 Ernest Rutherford from New Zealand, but at Cambridge, discovered protons when he demonstrated that materials like nitrogen gas, when bombarded with those alpha particles, those helium nuclei, emitted a hydrogen nucleus. And what is a hydrogen nucleus? Well, it's a proton. There's no neutron in hydrogen, which is a single solitary proton. And it was in 1932 that James Chadwick, also a Brit and also at Cambridge, bombarded beryllium with alpha particles, those helium particles. He bombarded, they were coming off polonium as the source, and detected uncharged particles that were being emitted. He discovered the neutron, 1932. Now, although Einstein's equation E equals mc squared, everyone knows that, was a theoretical key to the explosiveness of splitting the atom, there's a lot of energy in them, they're atoms. The mass times the speed of light squared. A lot of energy. But it wasn't the key to harvesting that energy was the neutron. It was the key, discovered in 1932. Nothing could be devised prior to neutrons being discovered that could split an atom and release all that energy. Anything with a positive charge, anything with a negative charge, positive or negative, would be repelled by the nucleus, by the atom, before it could even split an atom. But bombard an atom with something neutral, something technically not seen by electrons, not seen by protons, and it could pass on into the nucleus and split it to smithereens, the neutron. That was once it was discovered, it could enter. Now you got pure uranium-235 as the trigger in a nuclear bomb, and you got a larger piece of uranium-235, and those neutrons will instantaneously split a bunch of atoms and release, go Splitsville. If the uranium-235 isn't quite as pure, you got nuclear energy, and that's the difference. It is also interesting that some people speculate, because the neutron was discovered in England in 1932, but had Hitler in the 1930s not run out of Germany, nearly all of the nuclear physicists, most of whom were Jews, had Hitler's Germany discovered the neutron first before the Brits, Nazi Germany might have built a nuclear bomb long before the Americans, and you and I would be speaking German, eating schnitzel and sauerbraten. But anyway, two salient points about serendipity. Serendipity was at the heart of discovering X-rays by Roentgen, high voltage cathode tube. Serendipity was at the heart of discovering spontaneous radiation by Becquerel, the uranium, lighting things up. And it was Madame Curie that correctly theorized that spontaneous radiation was an atom giving up something of itself, which smacked against the indivisibility of the atom. But regarding serendipity and science and those two discoveries of X-rays and spontaneous radiation, it was Louis Pasteur who said it best. Chance favors the prepared mind. In other words, serendipity to discover requires a degree of knowledge in order to make the connection. My books, History of Man series, I have 6 out. This is the first one, First History of Man. It's a style of writing called jumping off. I have a base subject, which is medicine and science, and I jump off into history and sociology, geology, geography, art, music, sports, you name it. Always come back to the base subject and jump off. It's an interesting style of writing. It's not common, but I promise you, with the turn of every page, you'll learn something. The books are in print, e-Kindle, and audiobook, where I do the narrating. Anyway, I hope you enjoyed this episode of History of Man series. I hope you're well, and thank you for listening. Have a good day.